All right, hi everyone. My name is Andrew Pham, and today I'll be talking about amicable numbers. In this presentation, we'll be going through some history first, and then head into some preliminary tools that will assist us in understanding how Euler was able to find these pairs, for which we'll go through Euler's method, and then end off with some discussion on applications regarding amicable numbers. So let's get started. So contextual background and history information will be retrieved from William Dunham's award-winning paper on Euler's amicable numbers, which will go into more depth on the topics discussed here today. So if you guys have any question, I suggest giving it a good read. It's really concise. Anyhow, um, amicable numbers have been around for a very long time now, ever since 4th century BCE, where the Pythagoreans were able to find the first and smallest pair to be 220, 284, and saw that they had the unique property of where each number could be represented as the sum of the other number's proper divisors. Where a proper divisor here is the divisor of any number that excludes the number. So the divisors of 6, for example, is 1, 2, 3, and 6. The proper divisors of 6 are just 1, 2, and 3. Just drop the 6. But progress on this will halt for a very long time, up until 850 CE, where Ibn Khaldun will pick it back up and develop a method on finding these pairs using prime factorization. Unfortunately, due to the geopolitical nature and pillaging at the time with the warrings and stuff, conflicts, his work, along with many other Eastern mathematicians' work, would be lost and hindering the progress. But luckily for us, a few hundred years later, Fermat and Descartes in the 15th century was able to independently find new pairs, two new pairs each, adding to now three known pairs in the 2,000-year history. But the most influential part of this topic's history has to be in the 16th century. In 750, where Euler was able to publish his Des Numeris Amicabilibus, which discussed his method on how to find amicable pairs and how he was able to find 58 new pairs by himself, essentially increasing the pool of known pairs at the time by almost 2,000%. So very impressive by Euler. So let's see how he did it. So first we need to develop some tools. So first, define Euler's sigma function to be for any natural number n, and its divisor is given by di. Sigma of n will be the sum of all di. So for example, the factors of 6 are 1, 2, 3, and 6. Sigma of 6 will be 1 plus 2 plus 3 plus 6, which is 12. Another one, sigma of 3, since 3 is prime, it's going to be 3 plus 1, so it's 4. Turns out that primes can be generalized using the sigma function. So we can say that for any number p that is prime, sigma p will be p plus 1. All right, that's good. So another property that we want to look at is, what about the product of primes? What about sigma of pq, for example? So for sigma p that is not equal to q, for two prime numbers p and q, sigma pq will be equal to sigma p times sigma q. And we can easily prove this by seeing that the factors of PQ are PQ, P, Q, and 1. By the definition of the sigma function, we take the sum of those, and through some grouping and factoring, we're able to get 1 plus P times 1 plus Q. But by the prime representation through the sigma function, this is simply sigma P and sigma Q multiplied together, as required. Now, with all things considered, we can now define what amicable numbers are in terms of the sigma function. So, two numbers, m and n, are amicable numbers if sigma of m minus m is n, and sigma of n minus n is m. And if this, of course, is just the math representation of the sum of the proper divisors of the other number. And now if we add m over to this side and n over to this side, we'll get this nice uh, relation here. Sigma m is equal to sigma n if they're both m plus n. And given an example, we can confirm now that 220 and 284 are amicable, because if we take the sum of the factors of 220 that exclude 220, we'll get 284. And the same thing, we take the divisors of 284, except for 284, we'll get 220, confirming that they're amicable with each other. With that being said, let's get down to how Euler was able to do it. So, Euler's method, what he did was he assumed that there existed a pair, Mn, that is equal to APQAR, where PQ and R are different primes, and A is the greatest common divisor between M and N. He also let X, Y, and XY be as follows, and if you guys noticed, X is simply sigma P, Y is simply sigma Q, and by the product of primes theorem, you can see that sigma R is given by XY. That being said, what he did was he started with a value of A, so any natural number A. He solved for XY from this equation where B is this 2A minus sigma A. And then, if he found XY to yield PQ and R to be all prime, he'll take Mn to be APQAR as amicable candidates. But how did he get this equation? And what is this weird substitution here? Let's find out. So first, let's go through the derivation. We're going to let Mn be APQAR, and then let XY and XI be as such. So then, by the definition of the sigma function and the product of primes rule, we'll see that sigma m is equal to sigma a times xy. But since we assumed sigma m and n are amicable, we'll see that sigma a xy is the same thing as n plus m, which is apq plus ar, factor the a out. And then through the substitutions here, we'll arrive at this line right here. Now going through some more algebra, and then making y the subject, we'll eventually reach y is equal to ax over 2a minus sigma a times x minus a. Now, if we want to simplify the algebra now, we're going to let this weird quantity be some number b, and then consider the difference by minus a. Doing so, we'll obtain our desired result through some more algebra as required. So you can see here, there was no special techniques required other than, some basic algebra, and the variation was pretty straightforward. But now that we have a result, what can we say? What can we do with it? What even are amicable numbers useful for? And does this even work for all A? Well, it turns out that unfortunately it does not work for all A, and it turns out that is no complete, clear-cut way to find all amicable numbers, or any amicable numbers. Euler himself had to use different variations of this method in order to obtain more amicable numbers. Like he changed, instead of starting with Mn being APQAR, he said Mn was APQARS. So tacking on another prime number to n and such. Yeah, so there still hasn't been a clear-cut method yet. And with that being said, we still don't there's also an open problem with this topic, as in we don't even know if there are infinitely many amicable pairs. But what we do know from a study done by Allen and et al. Was that if we take the ratio of each amicable number and we increase the amicable number pool, we'll all soon converge to 1. So if there were an infinite number of amicable numbers, it would have to satisfy this limit. But other than that, amicable numbers today don't seem to have any practical applications. However, since they do use prime factorization, they contribute a whole lot to the advancement to uh, the field of number theory. And of course, number theory has applications, with prime factorization and all, especially in cryptography. So it's still very important to learn about amicable numbers. And it serves as an introductory topic in number theory, of course. With that being said, I will end it here. So thank you guys for sticking around and listening, and I'll see you guys next time.